Okay, so resonance is not something new. You know what resonance is, but there's some features, especially when we're talking about conjugated dienes, that resonance can give us that's something worth noting. So in every resonance structure, you're always going to have a major and you're going to have, I'll switch colors, a minor structure. And each and every one of these gives us unique, or does unique things. So with the major structure, this generally tends to have two properties that make it the major structure. It satisfies the octet rule, and I'll go ahead and write that down in a different color. And if it satisfies the octet rule, it tends to have more bonds attached to it, have more bonds in it. So this is what we use to, generally speaking, identify as a major structure for a resonance molecule. And there are two things that the major resonance structure determines. Major resonance structures determine both the shape of the molecule, the geometry of it, and the hybridization of the atoms inside of it. Some notes that I feel like are necessary to, I guess, put down about this as well, though, is that hold on, let me finish. Go ahead and connect these two here, both of these things, and wrote this out, and then I'm going to go ahead and talk about it now. Is that whenever you're talking about the major resonance structure, and you have, say, carbocations or carbon radicals or carbanions that are allelic, the only way that you can stabilize that or delocalize it is with overlapping p orbitals on both the top and the bottom. You must have effective overlap with both. So I guess if I were to try to compare this here, so you have a carbon here, and inside of that carbon there's say that it's allelic, so there's a carbon here, and say that this is a I don't even know, say a carbanion. It could be any one of these, though. If you say that this molecule here was sp2 hybridized, well, then that's going to be in a p orbital. So if this is a sp2, this p orbital is going to have effective overlap with the other pi electrons, or the electrons of the pi bond, effectively on both top and on bottom. So if we were to have that with sp2, let's compare that with an sp3 hybridized molecule. You're going to have really good overlap of a carbanion on an sp3 hybridized molecule. Really effective, that. But if you're to kind of compare these, and your book shows a really good diagram, or my book shows a really good diagram of this, but you're only going to get top only. You're not going to get overlap on the bottom face. And that's the point that I was trying to drive home with that. So that's with that. Now let's talk about the minor resonance structure. So I'm just go ahead and draw, why not, because we're figuratively talking here. This is the minor resonance structure, and in the minor resonance structure, this is what usually defines this is whenever you have, or I guess not necessarily minor, but the least important rule, number 2, your number 2 priority, whereas with the whole major definition thing, that was your number 1 priority. But it tends to be the minor, or at least structure that is where the electronegative atom is what gets. I'm going to go ahead and just erase that. It's where the electronegative atom gets the electrons / the negative formal charge. And usually the minor, or usually the number 2 priority, this is what determines the overall reactivity of your molecule, which is kind of crazy when you think about it. So I'll just use a ketone group as an example here. So for this ketone here, what's determining the shape, the hybridization, and the structure of that is the major resonance structure. This is the major resonance structure. However, I could also draw a resonance structure where I take that lone pair And despite breaking the octet rule, I go ahead and move that lone pair there. And remember, when you're drawing resonance structures, also, I don't think I mentioned this, but the location of the atoms doesn't move. So if I do this, well, what have I done? I have now made that oxygen negatively charged, and I've created a carbocation here. This molecule here is not very stable, and it's also going to be very, very reactive. And so this is kind of a distinction between the two. Also, make a note that when you're doing a resonance structure, the overall charge of something doesn't change. I'm going to make sure that this is, obviously that's a carbon that's positive, positive, negative, neutral charge. And this over here has an overall charge that's neutral.